on it for paper 2 on Monday. Absolutely. Okay, let's get straight onto it. We're going to talk about electrochemistry today. We're going to talk about the application of some chemical processes in industry. You know, those final chapters in the book, those things about electrochemical cells being applied to electrolytic processes, refining of metals, the chloralkali industry, which is a very important part of the industry. We'll get some questions that will touch on most of those things. Now, we're going to start off with a question on electrochemical cells straight. No frills, no fancies. Let's just go and have a look at it. It's a question taken from, let's see the Wacom here. It's a question taken from the February-March 2009. So I think this was February-March 2009 supplementary. And here it is. The discovery of electrochemical cells has revolutionized our way of life. Just think of all the things that run on little batteries. The diagram below represents an electrochemical cell. Let's take a look at it. Well, there's a diagram, and immediately you're going to look at this and you're going to say, something's missing. But all right, let's look at what we've got. What we've got here very clearly is a standard hydrogen cell. Standard hydrogen cell, where you can see hydrogen gas being bubbled over a platinum electrode. The platinum doesn't take part in the chemical reaction as such, but what it does is it allows hydrogen molecules to attach themselves to the surface of the platinum so that they can then react with the hydrogen ions, the aqueous hydrogen ions, which means that we've got a solution in there, an acid solution in here. And also remember that when we talk about standard, these are all standard cells, and we have standard reduction potentials. And the reason that it's called standard is because we control very, very accurately the concentrations of liquids, the pressure of gases, and the temperature. These things are always run at 25 degrees centigrade. So the concentration of my acid solution here would be 1 mole per cubic decimeter, and my gas would be run at 1 atmosphere of pressure. Now on this side, we have another cell, which is clearly a zinc 2 plus, where we have the zinc electrode in contact with aqueous ions, Zn2 plus ions. And we know, and this is the sort of thing that's going through your mind very quickly, is we know that this is going to be something, there's the reaction, plus 2 electrons. We know that there's going to be something like this going on. We also know that that isn't one way, this is an equilibrium, and depending on which way the equilibrium lies, that's going to determine whether this is more likely to give up electrons, in other words, go towards the left, to the right at least, or take up electrons and go towards the right. But that's going to come out in the wash in a little while. What we also notice, and we're almost certain to get a question about this, is that there is something missing here because there is not a complete circuit. Okay, there's a break in the circuit here. In other words, nothing would happen as it stands in this diagram. Look at the mess that I've made on it already. Let's see what the first question is. Name the type of electrochemical cell that converts chemical energy to electrical energy. Right, let's just have the camera here. We've got two kinds of electrochemical cell. We've got the one that converts chemical energy into electrical energy. Now, that's the kind of thing that you will get in your torch cell. And then you get the other kind, which takes in electrical energy and it stores chemical energy. For instance, in the case of purifying copper, you're storing chemical energy in the form of very pure copper, which is, in the case of the purification of copper, you're actually going to deposit pure atoms of copper on an electrode. And that is the same thing as saying I'm storing chemical energy in that particular form. In order to do that, we need to put in electrical energy, because remember, there's no such thing as a free lunch. If you're going to store chemical energy, you've got to get it from somewhere, and that's the electrical energy you put in. That's called an electrolytic cell. But the other kind of cell is the one that we're dealing with now, and that is where we use some form of chemical energy, where you get some interaction, say, between a zinc electrode and the zinc ions in solution and in contact with it, and some other kind of cell in the other half of this electrochemical cell. Remember, there will always be two halves. One will be an anode, one will be a cathode. But there we are using up chemical energy in order to pass a current, and that is electrical energy. So the kind of electrochemical cell that converts, what is the question, chemical to electrical, is called a galvanic cell. And Amanda asked me earlier, she said, isn't it got another name? Yes, it does. Galvanic cell or a voltaic cell, either of those would be correct. Right, let's go on. Let's see the Wacom again. If the electrochemical cell is set up as illustrated, there will be no reading on the voltmeter. Give a reason for this. Let's have a look at me again. The reason for this is that there is an incomplete circuit. So what would you do in order to complete the circuit? You put in what is known as a salt bridge. Now, in the salt bridge, we don't get electrons moving through the salt bridge, but we do get positive ions moving one way and negative ions moving the other way, and that kind of balances the charges in the two half cells.
Would this be from the hydrogen cell to the zinc, if we're going to put it in the illustration?
In this particular case, yes, it would connect those two. It would connect from the one to the other. And in this particular case, we are going to get electrons going from the zinc towards the hydrogen. Yeah.
Oh, okay.
And then the salt bridge will just balance out the charges so that the flow of electrons in the external circuit can happen.
Oh, okay.
Okay, good question. Right, let's move on. Write down the value of the standard EMF of this electrochemical cell when it's functioning. Now, to do that, you're going to use your table. I prefer to use table 4B. And you're going to see that the standard hydrogen cell, of course, has got a potential, a standard reduction potential of 0. The zinc electrode is minus 0.76. But remember that when you work out the cell potential, you're going to take 0, in this particular case, 0, minus 0.76, which means 0 plus 0.76. And so when you just write it down, it'll be 0.76 volts. All right, let's go on here. Write down the voltmeter reading when the net cell reaction